So welcome everyone. I wrote this class to start training solar students in National Electric Code. I've talked over the years with engineering managers, as well as entry level labor, as well as solar installers who never got into solar through traditional electrical training pathways about code. And they a natural inclination is just to start out with the solar section of code and be like, I'm just going to focus on solar, and it really robs you of a depth of knowledge of National Electric Code. So for 2 hours today, we're going to cover the basics of the first four sections of National Electric Code, not just as they apply to solar, but also just general building design principles, general basics, so that we can better establish our vocabulary when we talk with our electricians, when we manage electrical scope, and improve our system design as well. This should also serve as a good exam review. Sometimes, as an engineer, you're asked to take electrician exams and as part of the project sign off. Whether it's a contractor exam or a NABCEP exam. And a lot of the questions on these exams cover very important things. And so if our class covers very important things, then you should be able to do well on the exam as a exam prep for an electrical exam. So it's a big class, but the goal of National Electric Code is to improve your design game so that you can deliver safe and high quality installation projects and really push the boundaries of solar design. I think that's where building engineers really have to take the lead, as opposed to just a general solar installer. Is that general solar installers are just interested in either putting solar out in the field for utility scale or just quickly across a rooftop for a cheap and repetitive product. And with the right design, you can really kick your installations up a notch and increase their value, as well as their payback if you know when to make the right choice or not. Another very important aspect of managing your own projects is that if you want just a general electrician or general roofer to install the projects, you have to know every single nut and bolt of the design so that you can specify it and get it built in the correct way. So to get out of the kind of specialty turnkey business model, or to be that turnkey design build contractor, you need to have a broad understanding of National Electric Code. No bones about it. Solar, batteries, these are all electrical scopes, and they've been ignored in the past because electricians haven't been wanting to do these kinds of skill sets. Well, today is not 10 years ago. The solar industry, the battery industry are major job resources, or exponentially growing market in the case of batteries. A little bit smaller than solar today, should be much larger than solar in the future. Code itself is a little bit difficult to study because it's not a governmental code. Governments adopt National Electric Code, but it's actually a private organization subject to copyright, and that reduces my ability to provide handouts and direct copies of National Electric Code. And so even in this class, we don't have verbatim code. What I've tried to do is like reduced snippets and comparison snippets to make you more familiar with code. But hey, if you're especially taking an exam, but even if you're not, having a copy of National Electric Code is useful. And even though there are 2020 updates, and then there's 2017 and 2014, every 3 years there's a new version of code. If you go buy a 2004 copy of National Electric Code, most of it is going to be the same compared to today. They update code, but they weren't doing electrical work in an unsafe manner, by and large, just 10 years ago, 15 years ago. So, even just going online and buying a used copy of code is better than having no code book at all. The new code book, it runs over $100. If you're buying a used copy of code and you want to take it in for an examination purpose, the important thing is not to buy a highlighted copy or a marked up copy or a copy with tabs on it, just a plain copy of code that you can thumb through and refer to. I don't try to memorize all of code. What we'll say is code follows a pattern. More on that in a minute. But that doesn't mean that, if I have a specific question, even about very basic things, I enjoy having that manual copy of code at my desk to look up. As far as 2020 changes go, the biggest change by far is this new requirement for exterior emergency disconnects on dwellings for on-site energy systems. So many jurisdictions in the past have required external to the building disconnect switches for solar arrays on the sides of the building, so the fire department can come up and disconnect the system. And that's always been controversial. Mainly the problem is the installer forgets to lock the disconnect switch, and then that disconnect switch becomes a safety hazard because it's readily accessible. And many don't realize that if the disconnect switch is off, there's still power going into one end of it. It's just the other end that's off. So you put a disconnect switch on the side of the building, someone sticks their hand in, electrocutes themselves, that's a hazard. And it hasn't been part of code. And so over the past few years, jurisdictions have been dropping this external disconnect switch requirement because it's not a part of code. Potentially it's a safety hazard. It's certainly additional cost. They don't do it in other countries. Well, all that discussion doesn't matter anymore because we have to put these emergency disconnects outside the building. Okay. It's little things like that start to make the United States solar industry more expensive than other industries. But to some extent, you get value for that. I mean, it is nice when installed professionally to have this, knife switch disconnect to disconnect all things. Doesn't have to be a knife switch. Some utilities called a knife switch. Where that comes from, we'll get into in a minute. Sometimes knowing code and being able to educate the inspector on these things helps you get out of local jurisdiction requirements that aren't actually in code. Code has it repeats information in funny ways. Like it'll define what feeder circuits are, like power supply circuits, and then it'll go and define the rules and regulations for electrical service circuits, where services are what supply the building. It's a specific type of feeder circuit. And it's like, well, you're just repeating yourself, so they do try and make code with changes more compact, less repetitive, more clear. Let's see. Any other changes that are interesting? A new section for Ethernet cabling towards the end, and the later specialty sections in 800. Some energy efficiency improvements we'll be talking about, and then some the electric vehicle and the battery stuff is important. I've been kind of looking at this in class for a while because one of the main differences between National Electric Code and International Building Code with regard to batteries is that International Code allows the use of electric vehicle batteries for building power. And so far, NEC has been ambiguous at best about it, saying that the batteries have to be listed for purpose. And so that's, well, if it's made for an electric vehicle, but then it's connected to a building, can you do that? That's been unclear. So now they're kind of taking a step towards embracing electric vehicle batteries being integrated into the building. But fundamentally, National Electric Code tells us all of the rules of the game in the first 4 sections, which is like 75% of code. And then all the exceptions to those rules are in the latter sections. And so, there's general rules, and then if you understand the general rules, then the exceptions become a little bit easier to understand. If you have a little bit of knowledge of solar and you can say, okay, normal electrical design is this, but solar is a little bit different in this manner. So how do the rules adjust specifically for solar? Understanding where code comes from is reduces the brute force memorization that you would otherwise have to have when just diving straight into, say, the solar specific section of National Electric Code. And then, of course, if you're doing solar work, but you don't really know what a neutral conductor does or what, equipment grounding is really there for, you can get in over your head the longer you go in the industry without taking the electrical side of the work seriously. Some just basic definitions that are common. Accessibility, is the ability to reach something, as opposed to readily accessible. Readily accessible is without climbing or portable ladders. So, accessible, you can be up on the height, but readily accessible is not having to have like any extra equipment to be able to go up and grab it. One definition that isn't all too common, but what is utilization equipment? And utilization equipment, the main thing is it's not power generation equipment. Utilization equipment is electricity that uses devices that use electricity, like appliances. So utilization is not utility equipment, it's devices that use electricity. Generally, code is going to defer to local jurisdiction authorities, which might have additional requirements above and beyond code. So code is a minimum safety threshold. In New York City, they might say, we're going to have more rigid conduit requirements in our, 40-story tall buildings because they're 40-story tall buildings. So we want to make sure that the buildings don't burn down. It's a heightened risk. So we're not going to include EMT conduit. We need rigid conduit. Local authorities have that ability. National Electric Code is not like a federal code. Bonding is synonymous to grounding, except you can bond things without them not being connected to ground, and grounding might refer to a specific thing. But by and large, bonding and grounding is the same thing. There's continuous loads and non-continuous loads. Continuous loads are loads that are on for 3 hours or more, whereas non-continuous load, it's for less than 3 hours. A dead front is a box that doesn't have live parts exposed to it on the other side. So it'd be like a face plate on a electrical box gives it a dead front. So, which loads in here are continuous? Your refrigerator's running all the time, your air conditioner's running all the time, your dishwasher is not running all the time. The dishwasher is not the continuous load. Is solar a continuous load or a non-continuous load? It's not on at night, it's on during the day. It's not really a load because it's generating electricity versus consuming electricity. But if we were to treat solar as a load, and the general rule of thumb is if you have a switch, the larger power source, the grid side, goes into the grid side of the switch, and the solar array goes into the load side of the switch. Even though they're both, power resources. But anyway, if we had to deem solar power a load, would it be continuous or non-continuous? And the answer is it would be continuous because it's on for 3 hours or more, a day. It's on for, 4 or 5 hours, maybe 7 or 8 in the summertime. So Solar is whenever there's like continuous load versus non-continuous load constraints, solar is going to be treated to the like continuous load constraint. Some additional terms: branch circuit is circuit conductors between the final breaker and the power outlet. So we have branch circuits versus feeder circuits. Feeders are service equipment, power supply sources, the final branch circuit of the fuse and breaker. So branch circuits can be feeder circuits, but specifically, you would refer to branch circuits as kind of the final circuit to a power consuming outlet, whereas solar circuits would be feeder circuits. Power from one service panel to another service panel would be a feeder circuit. So the front part of National Electric Code has a lot of terms and conditions. I've kind of highlighted some things that, enclosure is a fence, a housing to surround and protect from accidental contact. There's a difference between fully enclosed and enclosed. A complete tube might be a full enclosure, whereas a wireway, like a wire mesh, might not, depending on how thick that mesh is, it might not be considered fully enclosed. Fittings are the bits and pieces, the little brown piece of the Tinker Toy set that all the pipes plug into. Fittings are all the various devices that connect conduit to boxes, and that can be kind of the hard part of the project, I think, as a non-electrician, is figuring out, all the right fittings, because they all have a label, they all have a rhyme, they all have a reason. Hopefully we'll understand these things by the end of class today. So there's the ground. There are arc faults versus ground faults, grounding electrodes, equipment ground conductors, overcurrent protection. What we're trying to do in this class is a little bit of a start to finish review of code, focusing on the most important things. So some of this is going to be a dry class, so that we go start to finish, so that it is more of a comprehensive code training class. But anyway, let's say arc faults and ground faults in the solar industry. Walmart sued Tesla. Solar City put a bunch of solar leases on Walmart stores. They didn't mention the installer of the solar leasing by name, but they said that Tesla had negligently installed, the manufacturer of the connector, but they said Tesla had negligently installed and maintained these connectors, and some of the connectors are not compatible with each other. And that's just, I guess what I would say in the context of there's workmanship. You need to make sure your connectors are compatible. They're usually compatible, but not always. There's a 600 volt connector and a 1000 volt connector. And if you're using the 600 volt one instead of the 1000 volt one, even if the connectors are compatible, that could create a safety problem down the road. And usually these solar connectors, these MC4 connectors, are compatible, but if they were to fail, what would be an arc fault versus a ground fault? Well, an arc fault is when the connection is kind of pulling apart and there's a little bit of an air gap, and that could just be stranded wires on a terminal, arcing across the terminal but still within the circuit, or a solar connector that didn't get fully properly installed, or sometimes the pin inside the MC4 connector, they installed two of the same pin rather than the male and female pin inside the connector. It's a common installation problem. Often with new hires, I will have the bags of these pins with two different people to avoid any possibility of the connectors getting confused. But once you put someone on point of making up these connectors, you give them both bags, they're doing it all day. If they're not being mindful of their job, they put the wrong one, then these two things don't snap together. Then the installer goes and plugs them, and he might think they snap, but they don't, and then they start pulling apart, and that causes an air gap, and that causes an arc fault. And arc faults could be good or bad. They don't necessarily are the current of the circuit. So if you're arc faulting, the circuit could still be operating, but you have this hot point in your circuit that could cause a fire. Nowadays, inverters have arc fault detection in them, so when you make bad MC4 connections, often the inverter will just no longer turn on, depending on the severity of the arc fault, though. Ground fault is not an arc within the circuit; it's a fault to ground. And so, let's say you're installing a solar array, and one of these MC4 connectors, you're doing good wire management as you go along and tucking them into the frame. Let's assume one of these, let's say your cable management crew is coming behind the panel installation crew, and a flash flood occurs, and they didn't get to some panels that have some connectors dangling down, in a puddle. Well, those connectors, that current could go through that puddle, and then it could touch, something that's metal, on the roof, and the question is like, well, do we want that current to touch the metal and then fault the ground? Well, that's better than having that live voltage up there, and then the thing that does touch it to ground is you. So we have metal, grounding of metal part requirements for the ground fault to occur through to ground to clear it. But if that power source is still operating and that ground fault is still running, we really need to pay a little more attention to what actually clears a ground fault. A lot of the safety provisions that have been added to solar have been about isolating the power at the module level itself rather than at the array level. Because once you get up to circuit level power, if you're ground faulting on the rooftop, it can be very difficult to actually turn that ground fault off. And there's been fires because of that. The causes of those fires have been addressed in code and design changes in other places, but nonetheless, the code has said, no, we're going to start isolating the power at the array itself. Okay, so let's assume you take a maintenance call and you have a burnt up terminal block, like this. That's caused. What we see is L1 and L2 on the AC side power, and we can kind of see that the electricity has been arcing from one leg to another. So that's kind of a different kind of arc fault. And so what caused this? Was the wire too small? And so more current flew through it than what was supposed to, and that caused the wire to smolder and burn up? Was it the heat from the inside of the conductor? Was the temperature of the inverter too high? Maybe it was an indoor inverter and it was placed on the south side of the building and it heated up too much? Or is it more likely is it a design issue? Did they use, it's a first generation product? Maybe their terminal blocks are too cheap. Usually it's a workmanship issue. In this case, the installer did not strip the cable jacket off according to the manufacturer spec. They stripped too much of that off, and then these cables land on these inverters right next to each other, and there's not much space in these terminal blocks and computer boards for one power source and another power source. So this is where your project budget gets wasted by not using electricians to do your electrical work. Electricians will have more respect for good, proper workmanship and wire stripping to avoid these kinds of installation issues. So here in the installation manual, we have very specific instructions about how much of the stripping to take off, and that's going to vary by inverter to inverter to inverter, and at different ports on the inverter, it could change as well. Now let's talk about our grounding system. What is the grounding electrode, the equipment ground, the grounding electrode conductor? All these things are different, but essentially the grounding electrode is the actual thing that goes into the ground, like the ground plate or the ground rod. The grounding electrode conductor is a special conductor, which is the final conductor in the system. This is like the main plumbing pipe that takes all your sewer from your house and gets it into the city sewer. It's a bigger pipe than the rest of the plumbing in your house. The grounding electric conductor similarly is the drain for your electricity. So you know how they say, like, if you grab on just a one power line and you're dangling from it, you're not going to hurt yourself. But if you connect to ground or you grab onto another power line, you'll hurt yourself. Well, electricity needs that difference in voltage to flow. And so this ground is literally the drain for your system that gives the voltage coming in from the power lines a path to safely establish a reference to ground so that you can use that voltage to run through your devices and use electricity. So the grounding electrode conductor is the drain for your home, and special care needs to be made to ensure that grounding electrode connection is good. I get scared on my grounding electrodes because I use clamps instead of welds to connect to this electrode. Recently I've been doing CAD weld for ground rods, and I really like how that process makes a much more secure connection. On mine, I will go and install like a secondary ground rod on the project site with a secondary clamp, just because I'm afraid of these clamps becoming insecure with time. Now there's another path to ground that's not the final grounding electrode conductor to the ground rod. The other one's called the equipment ground conductor, and that's what connects all pieces of metal on a home, on an electrical system, to the grounding system. And so it's a pathway for metal bits, the module frames themselves. If they start, carrying current from the solar array, they're grounded, and that electricity should be, rather than remaining up on the rooftop as faulty open circuit voltage that, you touch it could electrocute you. Instead, it's going to shuttle that electricity down to ground. Now, that's a bad thing. Bad things can happen when electricity is flowing to ground in pathways that it's not supposed to. Things can burn up, things can catch on fire. So it's not a great thing, but it's also better than undiagnosed fault, just staying there with nothing happening until someone goes up and touches a module frame and electrocutes themselves. So, just because you're installing these equipment ground paths is not, going to ensure safety. What we're hoping in that situation is during that ground fault that enough current goes through the ground path to open up the breaker, and that things don't burn up in the meantime. And so a lot of electrical sizing is like, okay, well, what size does that ground need to be at so that if this machine is faulting through that pathway, that the breaker will open up before the current in that pathway starts, catching so much heat that the metal that it's ground faulting through catches the building on fire. So can we interrupt the circuit before that happens? And breakers themselves have coils in them that, based on temperature, will open up the breaker. And so the more current that flows through this circuit breaker, the more strain there is on this, hinge. And once that current flows too much, it causes the lever to open up the breaker. And so what that means is a breaker, like a 20 amp breaker, it actually might be able to take more than 20 amps for a brief period of time, a minute or two, 2 minutes, 3 minutes, but once it starts flowing continuously, it'll open up. But it'll only open up at the maximum of its current capacity. And so, can more current flow through the breaker's rated ampacity? Can more current than what it's rated for flow through the breaker? Yes, but only for a limited period of time before it opens up. That might be. Anyway, what is the difference between a breaker and a ground fault, GFCI breaker? What is the difference between the two? Well, a ground fault breaker can open up before you reach the maximum ampacity of the breaker. So what does that mean? Well, imagine those ground faulted solar panel frames. Let's assume half the electricity is going where it should and the other half of the electricity is going out the system ground. You might not be exceeding the breaker rating. And so the breaker's never going to open up even though you have a ground fault occurring. And you say, all right, well, there's certain devices in certain areas, wet areas, kitchens, bathrooms, where we have to have additional protection relays. Now that technology affords us the ability to do so. And the way that this works is it's not just the spring-loaded heat-based thing that opens up the main. There's actually a little current monitor built into a computer chip inside these GFCI breakers that reads the neutral wire, the return path to that equipment. And so actually we probably need to go back a slide and talk about this neutral wire versus the equipment ground. The equipment ground is not where the power should be flowing back to ground. The neutral wire, this neutral, there's one point on the system where that neutral is connected to ground, and that gives that neutral a 0 reference point. But whereas the equipment ground system carries that electricity back to its 0 voltage potential during a fault, the neutral wire is what carries it back under normal operation and then to ground. So, it's like if the difference between driving on the feeder lane to the highway and driving on the shoulder, you're supposed to be on the road, not off the road. If you're driving on off the road, something really bad's happening. At any rate, that becomes a little more real because now the return circuit for the circuit, that current is being monitored with, what's the equivalent of an electrician's amp meter. It says, there's some amperage that's unusual, or maybe there's not enough amperage there. It's that's supposed to be there. And so what it does is it's detecting ground faults that are smaller than what the breaker rating is. So they cost a little bit more, and they can in fact detect ground faults that are below the breaker rating size and flip the switch that way. So they're very useful to eliminate the safety risks of ground faulting circuits that are where the ground fault is less than the breaker size. And so in my experience, the breakers trip for a reason. It's not that it's a faulty breaker, it's that there's something real with the electricity that is physical, that is going on, that's causing the breaker to trip. It's not like an electronic glitch. And the mechanical failure of the breaker is rare. So, on this inverter that broke up, I had a customer, the inverter broke up, and the arc fault on the terminal strips, the wire was stripped too long, and that caused the fault. Well, initially the breaker tripped, and the customer turned the breaker back on, and then the arc fault occurred further and did more damage to the equipment. The inverter needed to be replaced. If that breaker had tripped and you took a step back and said, okay, well, there's 90% chance that there's something electrical wrong with the system, and so we need to figure this out before we let the system just continue to operate. Not letting those, this is real safety work. You can't just let a breaker that's tripped go uninspected. And so we had arc fault occurring, and it was on the AC side. It wasn't on the DC side. So the inverter's arc fault detection on the DC side of the circuit wasn't triggering the inverter to turn off. And, it was also something that the inverter's not really inspecting for, which was the workmanship issue. And what's frustrating about, especially these specialty components, is even though it's just one computer chip on a broader system, most solar manufacturers do not let you just replace the one chip. They will have you buy a whole nother inverter. So little small workmanship issues can be very expensive. I've never had a bad time with a project where it's been appropriately budgeted to have electricians, highly paid electricians, doing the electrical work. It always works out. It's just a matter of project organization. How well organized can you get the project so that the electricians don't spend a substantial amount of time on site? Of course, hazards occur for other reasons. A nail that's driven into a wire, is that going to be an arc fault or a ground fault? If that wood does not have enough resistance to establish a path to ground, you're just going to get some arcing as those strands of wire are, have a little bit of an air gap compared to that edge of that nail. And so you'll get a little bit of arc faulting across that nail. And that's much more tricky to detect than a ground fault, by the way. And so, arc fault current detection is a relatively new thing in terms of breakers and devices and NEC requirements, for that matter. All right, some additional vocabulary terms. Listed versus identified for use. So listed is actually evaluated and published by a acceptable organization. There's no requirement in code for UL listing. It just says listed. So many jurisdictions, government projects, commercial projects will say it has to be UL listed, but that can really limit your product selection, including battery products, because let's face it, the rest of the world has more expensive electricity than the United States, and so they're more on top of the game when it comes to advancing solar and battery electronics than the United States. And so sometimes especially with commercial batteries right now, your commercial battery inverters are all listed with like European listings. Maybe they have a European listing that is equivalent to the US standard, but that is something where you might have to go to your local jurisdiction to say, look, we're using an ETL listed device. It's not UL listed. We just want to make sure that that's okay at the planning stage rather than the commissioning stage. In sight from is visible and no more than 50 feet. Let's see. So we've in the past, there's been terms that have been really confusing, like a standalone mode or a utility interactive mode. Now we're calling an island mode is for off-grid, standalone, isolated, one-way power. And interactive inverters is for in parallel with, which means hardwired into, not operating alongside of, but hardwired into the electric utility as an interactive system. And so you might have an inverter that on one side it's an island mode, and on the other side it is a one-way charger. And so, being able to tell the jurisdiction if it's an islanding inverter or an interactive inverter, that's something that they might need a little bit of education on, because they're thinking anti-islanding, and it's, an islanding inverter is all right, but it has to be truly isolated it has to be truly islanded. You can't have an islanded inverter that is still connected interactive to the grid, because if the grid's down, first off, your inverter is going to output all of its maximum power directly into the ground. And if that ground is where utility linemen are working because it's a downed power line, you could kill them. Dry, damp versus wet. Damp is the hardest one. Damp is sheltered but still moderately wet, like under a porch, under a carport, protected from rain but still exposed to a lot of moisture. Whereas wet would be, you can still have a wet being underground slabs, saturated with water, or unprotected exposed locations. In slabs means actually within the slab itself, not in a basement. So attics are dry locations, rooftops are wet locations, basements are dry locations, but not all basements are dry locations. Some basements might be damp locations depending on, if the water's coming in from the wall. And so just some more basic words you need to know in this industry. There's supplementary overcurrent protection, which may not be the main overcurrent protection device. So you might have a solar circuit that's landed on a breaker, and then you might have module level regulators. Those module level regulators would be supplementary devices that are in addition to the main breaker. Sometimes that gets you out of oversizing requirements that are unusual or specialty oversizing. So you always oversize. In specialty cases, you'll double the oversizing. If you're using way more overcurrent protection than what's code required, if you're using supplementary overcurrent protection, then that extra oversizing step may be exempted. Panel boards are your main service panels. Those panels with a bunch of breakers on them. It can be more than that going on inside them. Switchboards, are generally just larger than a panel board. Let's see. Raceways are the channels that hold the cables going back to the through the house. Not all cables are required to be in raceways. Romex AC cable is not required to be in a raceway. DC cable needs to be in a fully enclosed metal raceway. So, and then lastly, there's sealable equipment. Means of sealing or locking so that live parts cannot be made accessible without opening the enclosure. So a box with a hinge, lid, and a lock would be sealing the equipment. What's kind of interesting about this, NEC says reconditioned is what we're calling refurbished, remanufactured, rebuilt products. It's reconditioned. And I think this is interesting. The IRS ruling says that you can actually count some used property as new in terms of qualifying it for the investment tax credit, provided that there's rules governing when the property was put into place, and that no more than 20% of the facility's total value is used. So that's kind of interesting. Potentially, you could do a used lithium-ion battery project using used electric vehicle batteries and still qualifying them for the solar tax credit if everything else was used and those batteries were only 20% of the system cost. Separately derived, basically, islanded systems are separately derived. Uh, there's the service cable, the power coming into the building, the service cable drop underground overhead where it comes into the building. We talked about standalone systems, which are now called islanded systems. Then we got surge arrestor protective devices. Let's just keep getting out of this and on into code. Okay. Electrical equipment needs to be listed or labeled or both. Not necessarily the same thing, but by and large, the equipment needs to be listed for purpose. You can't go and use electrical equipment that's listed for one thing and then just go use it in another thing. Where that really gets you is like, if you have underground cable splicing for inline splices, you may want to use those up on the rooftop in your conduit for some inline splices. You got to make sure that the temperature ratings are correct. And if they're not correct, an underground temperature rating might just be for 60 C and not 90 C, and you go put it on a rooftop, then it messes up your temperature calculations and you cause a fire. So, there's reason for this. I think one of the most commonly overlooked aspects of the design is that code actually requires you to use a torque wrench to torque your connection points to spec. And so most installers, myself included, really will use, adjustable powered wrench or drill to, tighten our fittings. There should be a person on site with this torque wrench who knows how to use it and is looking up the torque wrench values and putting it to the adjustable setting and then following alongside them, ensuring that all the values are tightened to spec but not over tightened. So let's see. Torque wrenches nowadays are not that expensive. Finely precise ones or power tool activated ones are, but just the drill on itself, even if it has that screw setting for torque, it's not giving you a precise torque value. And with these electrical connections, you're building these power systems, it's no slouch. You don't want these connections to come apart and work themselves apart. You don't want to over tighten. You don't want to crack any terminal blocks. You don't want to crack any chip boards. You don't want to bust the actual cable so that it pushes itself out of the way, but you still need to get it, tight enough. An installer, a professional installer, might err on over tightening things more commonly than under tightening them, but an amateur installer is going to under tighten them. And they don't have the hand strength of a worker. So, spaces about electrical equipment. So, electrical spacing is required around all electrical equipment, where basically no non-electrical equipment should be in that zone. There's a specific zone, and actually the only thing that's wrong with this picture is that they've managed to get the 6.5 foot height requirement, and they've kept the gas line and water line like out of this electrical space. The only problem is they've stored stuff in front of the service panel, and you're not allowed to have that storage there. But despite the messy appearance of this room, it is compliant. The areas where people mess up is like there's a working depth requirement that's not just the workspace. So the working depth requirement is 6 inches. So there can be no more than 6 inches of space between the front of this panel and the front of this battery, because otherwise you have to lean over the battery to get to the equipment. And so there's a 6-inch depth requirement. The width requirement is really easy to the point where you don't really even ever worry about it. It's 30 inches minimum, and that's it. And so basically, your electrical equipment you have to be able to stand in front of to work on. And if you can stand in front of them to work on them, then you have enough equipment left to right. Height requirements 6.5 feet, a little bit taller than the typical person. When I'm thinking about layouts for rooms, the good rule of thumb that I've come up with is: can you imagine being the person standing in front of the equipment and safely and comfortably operating on it? If the answer is yes, then you're probably not violating any code. And if the answer is no, you probably are violating code. Battery rooms have to be lit. They can't not have any lights in them. You can't be shoved up against a wall here. And in fact, the space that has to be storage free and kept away from stuff, that space, that dedicated space on the floor is shorter if there's nothing behind you, which is a weird concept because like there's nothing behind you, so you have infinite space, but that dedicated space only needs to be like 3 feet. If you have a wall behind you, it needs to be 4 feet. Oh, sorry, it needs to be it ranges between 3 to 5 feet, and it ranges between voltages as well. And so generally, if you have a wall behind you, it needs to be 3.5 feet. But if it's other electrical devices behind you, so if it's not an insulated wall, but it's other electrical equipment, then you need to have a 4-foot range in a typical room. But if you go into commercial 1,000-volt systems, all these requirements get harsher. And so instead of a minimum 3 feet, maximum 4 feet, it's a minimum 3 feet, maximum 5 feet, depending on, you're standing in the room, what is behind you. And so where I kind of memorize this thing for an exam is, the standard is you need to have 3 feet of working space behind you. If you have a wall behind you, that's even more than that. If you have electrical equipment behind you, it's even more than that. And so, and then I don't worry about the 1,000-volt stuff because I'll say, okay, if any exam I'm taking, if it's 1,000 volts, I'm not going to guess. I'm going to open it up and look because there's going to be harsher requirements than normal. And that's depending on, what's behind you. Is there anything behind you? Is there a wall behind you? Is there electrical equipment behind you? Will increase that space. But the standard is 3 feet behind you, more if there's actually something behind you. So thinking about things like dedicated equipment servicing space, should there be 3 feet between rows of panels so that you can walk up and down and service this equipment? I guess you might argue that the equipment doesn't have any serviceable parts during normal operation. There's no breakers, there's no boxes, but I don't know. There are connectors. I haven't seen anyone enforce a 3-foot requirement on row spacing, but if you wanted to be fancy, like if you were designing, not just one row of modules with a little short shadow, but something with a higher tilt or something with a longer space, that electrical spacing that, if there's 4 feet behind you, that would allow you to actually get down and crawl underneath this array and get back out without, bunching up against the module. If there's no spacing in between these things, you're going to have to, Spider-Man across the array, and that creates a tripping hazard, a falling hazard. It's just not as comfortable for a worker. So in terms of spacing requirements and minimum spacing requirements and maximum spacing requirements, if you're looking at it with consideration to the worker to have enough space to safely and comfortably work in that area, you're generally compliant with work requirements and spacing requirements. Now, most solar arrays on like roof mounted projects are only spaced apart by a foot or two, but you're not really supposed to be walking through them anyway. do a good enough job on the installation side, and you really shouldn't have to, except for very unusual circumstances. But that requires you to do a good job on installation. Let's see. So we've talked about dedicated spacing. Locked equipment is considered accessible. When you get into higher voltages, higher amperages, heavier power systems, the protection requirements get even more robust. So in high amperage rooms, you got to have a door that opens outward. Kind of weird stuff like that. We're going to take a break right at the top of the hour for about 10 minutes, but since it's we're rounding the halfway point, let's just keep going. So it says listed inverters shall not be connected to premise wiring without a grounded conductor, or shall be permitted without a grounded conductor, where the premise wiring includes without a grounded conductor where it includes wiring or utility system. It includes a grounded conductor. What does that mean? Okay, well, not all 240 volt electrical devices have a neutral. The neutral is kind of there for imbalanced loads, but 240 volt devices made up by 120 split legs will function without that neutral path, provided that the load is perfectly balanced. I don't want to get into what all of that means. I just want to kind of cheat and tell you that some air conditioning units don't have a neutral. And so we have this feeder circuit providing power to an air conditioner without that neutral conductor. And the question is, could we take this switch off the wall and put a panel board there and tie a solar array into the panel board and tie the air conditioner into a panel board? And where that might be neat to do is if you put in a utility, maybe even just a one-way inverter to back up the air conditioner during a power outage. Or it could be a bidirectional inverter to also generally assist the rest of the building, although that's more complicated to do. And the answer is yes. You can find utility listed grid interactive solar inverters that are for 240 without a neutral configuration. So you can wire some of these inverters without the neutral on that air conditioning circuit. It's kind of an advanced I've never actually done this before, but it is possible. So sometimes I'm thinking about like small solar and how to incorporate a small solar project onto a site without much muss and fuss. And the answer is, well, there is that disconnect switch location where air conditioners come into the building. If you wanted to just throw a 4 or 5 panel system down on the ground with a small, even a cheap lead acid battery, just to provide some backup power to your AC or otherwise reduce your AC system usage, there are opportunities for grid tied, lower end, lower cost projects down on the ground that installers aren't even caring about right now. Okay, so some things to know. DC circuits, once they get over 60 volts and once they get over number 4 AWG, and most solar is less than that, they can be identified by tape as positive or negative. So solar circuits that are under 6 WAWG that are not the grounding conductor, the positive should be red and the negative is black. Sometimes white. Dwelling units, there's minimum branch circuit requirements for each room. Arc fault current interrupters, kitchens, family rooms, dining rooms, as far as bathrooms now, the latest update is it's within 6 feet of the bathroom itself. So now they're saying, arc fault current interrupters on, say, the bedroom side of a bathroom, if it's still within, if it shares the same wall as a sink, for example. In the interest of time, so we're starting to get into some ampacity requirements. We have this, it can be rated for the non-continuous load and then 125% of the continuous load. Remember, if we're talking about ratings and amperage ratings, the non-continuous load is only on for a shorter period of time, whereas the continuous load is on for a longer period of time, and that's going to generate more heat inside those wires. So to make sure that our wire ampacity is rated for the appropriate size, we find our ampacity, and then we say for our ampacity for the circuit is this much, and so our wiring has to be 25% larger so that wiring doesn't burn up. And so a good rule of thumb for any electrician exam is just to take the ampacity requirement of the device, multiply by 25%, and you're at the ampacity size for the wire, and then you either round up to the nearest breaker or down to the nearest breaker, as we'll see in a minute. Now, specialty devices like solar may have additional ampacity requirements. We're going to be talking about that more tomorrow in our solar specific class. So this says, if the total assembly is listed for 100% operation and it includes an overcurrent protection device that's listed for that assembly, then the extra 25% requirement drops out. So you can have devices that are like manufacturer labeled for fuse size and fuse ratings, at which point you can just use the manufacturer provided size. So in general, our load is going to be, there's less load on a branch circuit than what is on that breaker rating. So if you have a 20 amp circuit or a 20 amp breaker, the maximum load that you're actually allowed to have on that is less than 20 amps. So that your load in those 20 amp branch circuits, if you have a 20 amp branch circuit for microinverters, they're only allowed to get up to about 16 amps before you have to go on to adding another circuit or breaker. So that within that 20 amp conductor on that 20 amp breaker, you only get up to about 16 amps of operation. If you got all the way up to 20 amps operation, then the breaker would trip and it wouldn't be a very good system because the breaker would be tripping all the time. Let's see. So larger appliances, 40 amp, 50 amp breakers, on more often than not on dedicated circuits, there's different loading requirements versus if you have full-time hardwired devices that are on lower amperage breakers and ratings. So the larger you get, the kind of more custom specific the rules become. Whereas on the low end of things, the 15 amp, 20 amp, you have a lot more kind of fudge factor or intentional wiggle room in that outlet. There's spacings for receptacles. This kind of general home building knowledge, we're going to not get into as much detail and just leave it to you after class to kind of read through. Outdoor outlets, there's a requirement now to have outdoor readily accessible power at the front and back of dwellings. So throughout code we see, this general, hey, the rating, the circuit overcurrent protection device needs to be rated for the continuous load plus the non-continuous load plus 125% of the continuous load. in general, the cables and conductors have to be in the same enclosure, not separated. The characteristics of those enclosures have to be the same as well. So if you're doing parallel wire runs and dividing up the cables into those parallel runs, you have to have positive, negative, and ground in each run. Where the premise wiring has feeders from more than one voltage, each ungrounded conductor shall be identified by phase or line at all termination, connection, and splice points. Now we see solar labeling and conduit requirements, but this is just saying, hey, any kind of feeder conductor, if you have multiple kinds of feeders, you need to label, you need to label the feeders to say what's going on. Here's one that's kind of, I thought was useful to know. The fractions of an ampere. National Electric Code's a fudge factor. It's so that you don't need engineering data. And so they say you can calculate the amperage to the nearest whole amp, rounding down or up. You don't need points. In fact, our voltages are much more fluctuating than their nicknames would suggest. So on 120, 240 residential service out in rural areas, it can easily get up to over 250 volts at 125, 126 volts per leg. It varies from utility to utility. It varies with the society's electric load, how much power and the distance of the power. These voltages are just conventional nicknames. As far as generating how much power should apply to a house, there's load calculations. So it says, what do you need to do? Well, for dwelling loads, this has changed a lot, right? Because LED lights are very different than incandescent lights. And so one of the major changes to code for 2020 has been a reduction of the load calculations. What we can see here is that, you might calculate all the demand for a building and you don't get any deduction. But if you get into multi-unit buildings, you can say, okay, well, you get a little bit of a reduction factor because not all of the homes are going to be using all of their devices at the same time. And that kind of averages it out. So the larger a building gets, the less harsh these demand factors kind of become. What that also means is that an apartment building or a hotel does not have the power capacity in its system for everyone to be using all the devices all at the same time. And so these lighting load tables in National Electric Code for 2020 have been substantially reduced for 2020. So home load calculations, building load calculations should be reduced for 2020. What I think is also interesting is it says you don't even have to use your calculated load calculations if you have automated energy management going on site. And so whether it's solar or batteries or just digital load controls, which we talked about in a PDH Pro class last week, that's now available on demand, taking proactive measures to manage your building energy load might be able to help you if you're doing a large building with a very small power supply, because that's all the utility can provide you to be compliant with code. If you have a larger load on site than what the utility is capable of supplying, implementing some load management on site can get you out of that requirement. So there are minimum load requirements. So the minimum load that a home has to be able to be rated for is 10 kilowatts plus some additional factors. So this is like your starting out bare minimum. And what is a 10 kilowatt load? That's about 40 amps. And then on top of that kind of minimum load, you also have to add, this is for other loads. So the way that the load calculation kind of works itself out is you add up a bunch of different load assumptions. Anyway, code is not trying to be too harsh here. Code is saying if you have loads that are on at different times, then you can use the largest of the two loads for calculating the load requirements. So, what is your load with your air conditioner when it's in your cooling mode? What is your load for your air conditioner in heating mode? You use the largest of the two loads for calculating the feeder size or service. Usually on air conditioners, that's the load of your electric heat tape that's been built into the indoor unit of the unit, which could be as much as 15 kilowatts. I usually tell my off-grid customers learning the hard way to intercept that at the get-go and specify the 5 kilowatt heat tape. Let's see. So we start to get into load reductions for larger programs, larger devices. Let's just keep going. Now these power ratings, 440, 208 3-phase, 120 240 split phase, that literally has to do with the physical wirings of power that go into this utility transformer that convert kind of higher voltage distribution power into lower voltage building power. So, whatever that distribution circuit is feeding, they get a transformer hanging on, and that electricity spins through these cables, and the voltage and amperage is manipulated that way. It's easier to do with alternating current rather than direct current. That's why our grid is built out with alternating current. But I guess what I'm trying to say is 120 is different than 120, 240 is different from 240. And so like a 240 volt pure electric service will have a 240 volt leg, and then it's tied to ground. 120, 240 has two separate 120 volt legs that if connected together can give you, because of the AC nature of alternating sine waves, can give you 240 volts. Or you could just run your whole house off 120 volt circuits, and that's common for small homes like individual one bedroom apartment buildings might only have a 120 volt service. At the commercial level, they have a delta service and a Y service, and that's literally has to do with the windings inside that transformer forming a delta triangle or a Y in their windings. And so you'll have to get a different inverter for each custom kind of electric service, or sometimes there's dip switches on the inverters that you can select to make one 120 volt or 120 240 or just 240, but that's more rare. Usually you got a common one is people are looking at commercial systems, and you have to kind of start out with, okay, am I doing a 480 volt commercial system or a 208 volt commercial system? That will impact your product selection for inverters, for example. And so here we're doing our residential load calculation. We have our base load of 10 kilowatts, plus our lighting load, plus our small appliance load, plus our air conditioning load, and we get to our final load. And essentially the smallest that you can do a dwelling is a 25 kilowatt, 100 amp service on up from there. Or you can collect the load data for 1 year and use that load data. And where that might start to get useful is larger houses where you might have to be installing 200 amp service panels to land all the breakers. And you say, well, do I need to have 400 amp service from the utility? If you just use generic load calculations and count up all the devices and all the circuits, the answer is yes. But if you have load data from either the existing home and you're doing an expansion and they want you to upgrade your service, or you're implementing kind of load management devices, you can say, no, I can just keep it with my existing service. Sometimes expanded services cost more, sometimes they don't. Depends on the utility. Okay, overhead conductors have clearance requirements, and it's overhead conductors have an 18-foot clearance requirement for driveways. Those overhead conductors need to be 18 feet up in the air and 15 feet for conductors that are in excess of 300 volts. I get really concerned about solar carports that are not, 18 feet tall, because potentially that's a code violation. There's ways to do carports at 150 volt circuits instead of 300 volt circuits. So there's a lot more wiring, but that might be a reason to do so, is because there's cars and people, underneath that could hit those posts, and, limiting the voltage is going to limit the damage. Above rooftops, your overhead conductors have to be 8.5 feet, but that's assuming that there's no pedestrians underneath the rooftop as like a rooftop deck, which gets you back into this substantially elevated platform. So, I really like solar pergolas in that concept and the way they look, but I fear they have to be much taller than what many installers, a 6-7 foot, 6.5 foot clearance requirement. Really they should be, to be code compliant, 18 feet tall for these 600 volt systems, or solar pergola doesn't need to be that big. Maybe you step down and do 300 volt circuits, or even less than that, to not have this clearance requirement. Now, a lot of time inspectors don't even think about this stuff because they don't see it in residential inspections, but I don't know. I guess I was cut my teeth in solar in areas where the inspector, if they could find anything that was a violation, they're going to point it out to you. And, that can be a good thing. It's not there for no reason. Finally, it's like, well, how about where I look out the window and I'm in a city and I see a rat's nest of wiring just a couple of feet from the windows. You have to stay 3 feet away from the windows for that final span of those overhead power lines going into the property, except for the very top window of the very top of the building, where your feeder conductors can actually just go just above the window. The premise is, even if that window is open, what you're trying to do is prevent people from opening up the window and waving their arms around outside and electrocuting themselves. So raceways on exterior surfaces need to be arranged to drain. That means like when if you have solar conduit, here's your rooftop, and you have solar racking that is running across the roof east to west. How does that drain? If you're depending on your cable management system, if you're putting the cable kind of inside in a U channel where there's a little trough that these things make, you have to make sure that trough doesn't fill up with water. So, you're going to have to go and modify your solar rail and drill holes throughout it so that the water drains out rather than pools in. Not all rail is the same. I prefer the trough method of solar because it provides good physical protection against debris and against rodents, which is a different kind of hazard. But even so, you need to arrange the cables to drain. If you have a module level box and it's up on the rooftop, you can't go into the top of the box where water could be getting up and into the box. The best connection is to go into kind of the bottom side of the box. So here's your cables coming into the box, and any rainwater will just slick off the water rather than go into the box. So all of your raceways and the wires and the outside of conduit, for that matter, cable, need to be arranged to drain, as well as listed and approved for wet locations. Sadly, you're not allowed to use trees as a support to your solar panels. If you're in a big field, a pinewood forest, trees can get very tall, and you might start scratching your head and say, well, why can't I put my solar way up there? Even with the level of safety protection that we have with module level panel electronics, there's no exception. You can't put solar on trees. Here's a common exam question, the raceway seal. When entering a building from the outside, it shall be sealed. Like, this is whenever you go from a temperature differential, from one temperature to another temperature, with a conduit, you need to seal that conduit with spray foam, sometimes fire-rated spray foam. Depends on what kind of wall you're going through. But at bare minimum, you need to seal up these conduits because the condensation from air in the conduit itself can cause it to rain inside your conduit. And so a common electrician's exam question is like, if you're going from a refrigerated room to a non-refrigerated room, no matter what it is, it's like, oh, that's a sealing question. The conduit needs to be sealed because we're talking about two different temperature differentials. That's from the attic to the roof, from underground to inside the house, from outside the house to inside the house, from a refrigerated room to a non-refrigerated room. You need to seal the conduit. So how much power can supply a building? Can you have multiple services? And it says, well, if you have a building, you're supposed to have one service, but then there's exceptions. Very large buildings can have multiple power services going into the building. And then there's all these other exceptions for on-site energy stuff, emergency backup and standby systems, fire suppression systems, solar, batteries, electric vehicles. They're given all sorts of additional exceptions to say all these things can supply a building. Generally speaking, you can group your on-site power systems together and not get into an issue with that. I mean, code is pragmatic. But that actually gives you more flexibility on where you locate these things rather than less flexibility. The general rule for establishing service panels and power distribution panels and all that is if you have more than 6 handles, this is called the 6-handle rule. If you have more than 6 handles for controlling a service panel, then you need to have a main breaker on top. So sometimes you get these service panels that don't have a main breaker, and they're intended to have 6 breakers or less on them. Kind of no matter where they land, you should have, you could have 6 240 volt double pole surface breakers, and now that fills up the whole thing. Once you have more than 6 handles, you need to have a main breaker on top. If you have less than 6 handles, then you don't need to have that main breaker on top. And that's why you have some panels without one that are smaller and other panels with one that are larger and more expensive for that matter. I think there's a lot to be said for 100 amp cascading distribution panels that kind of feed off each other and power a few things and then go on to the next one, all having their own kind of one-way battery inverters for simplifying component selection and ultimately reducing project costs. Maybe down the home of the future is a 200 amp service because we have all this on-site power that says we don't need more than that coming in from the utility. But then the 200 amp service panel is really just there to break out into smaller, 100 amp service panels for a variety of smaller on-site battery systems and isolating automatic transfer switches and stuff like that. All this stuff gets really expensive when you get into above 200 amps and really above 40 amps for that matter. Disconnects do not need to be breakers or knife switches. There's other kinds of disconnects. There's other kinds of breakers. Usually the knife switch disconnect requirement is a jurisdictional one. This says feeders and services should be identified at each disconnect location, saying what's going on. So the solar labeling requirements at disconnects is not really a solar thing. It's really a all electrical stuff. With disconnects should have some kind of plaque or map that says what's going on with this. Disconnects need to be either manual or power activated with a manual transfer switch. That's one of the biggest differences between US code and overseas. Is overseas they let you just get away with electronic controlled relays as your transfer switches. It gets much more expensive and complicated when you have to have a manual override. In addition, basically you have to have an automatic transfer breaker and in line with a manual override as well. It's just more costly. That's how it is. The disconnect switches need to simultaneously open all ungrounded conductors of the system. And so you'll get 2-pole or 3-pole disconnect switches, plainly indicating whether they're open or closed. And usually that means, if they plainly indicate, there's usually up is open and down is closed, up is on, down is off. Here we have the basis for that knife switch disconnect. It says for circuits over 1,000 volts, the switch needs to have a visible break, which means you need to be able to look inside with a breaker, you can't see the disconnect. You can't visibly inspect it. They want to say, okay, well, whatever disconnect switch you're using, the inspector should be able to at least open up the box and look inside and see that it, in fact, is capable of disconnecting in the off position. That's over 1,000 volts. So now at the residential level, this has been kind of co-opted to say you need a visible disconnect at the, for your solar disconnect as well, even though it might not be over 1,000 volts. What for circuits over 1,000 volts, uniform position, up is on, off is down, except for double throw switches where the middle position would be down. Service conductors should not be combined with non-service conductors. What that means is like your on-site power system circuits should not be combined with your load circuits. Now it's like, well, wait a minute. You just told me earlier that if you have a electrical distribution panel and then there's a 240 volt circuit feeding another distribution panel, maybe one that's not a main breaker switch, and then you have your, floor mounted air conditioning unit outside the house. Outside the house here. I said, well, maybe you could intercept that disconnect switch and put in a service panel and then connect a solar array here. And then you have your air conditioning unit connected here. And isn't that combining your load and supply service conductors? Well, no, because right here at this point, this is a feeder conductor. Combining the two would say, take here's your solar array. Sorry for my scribble, but here's your solar array. And we're going to combine the two by tapping it directly into the air conditioner conductor. That's not what we're doing here with our service panel. We have a load panel, and provided that we comply with all the rules and requirements for interconnecting solar on load panels, we're fine. And even though that electricity is commingling at the feeder, that doesn't matter. But you can't just say, I'm running this circuit out to the air conditioner and I'm going to throw my solar cables into the same conduit, the same raceway. You need to separate them. The exception being anything that's kind of related to the project, related to that solar array, can be shared the same raceway. It's not to say that that's a good thing. Just because you can put your communication cables into the solar conduit doesn't mean that you don't need to have shielded conductors or enough spacing to allow for adequate communication. It's just that you can. The size and rating shall not be smaller than number 8 copper or number 6 aluminum for services. Technically, solar conductors are not services. Technically, solar conductors are photovoltaic output circuits. So you can have solar circuits that are smaller than number 8. I think number 8's a pretty good size. Number 10, the voltage drop is usually right on the edge to where number 8's worthwhile. And heck, I often will go up to number 6 just because of balance of system material selection. Clearances, above the roof, not less than 8 feet. Well, code just said not less than 8.5 feet. It's a discrepancy in code. It happens from time to time. 15 feet for over 300 volts. Service entrance conductors should be protected from physical damage. And so there's more robust EMT to protect from that. So service entrance conductors do not need to be in conduit. They can just they're outside a conduit, wet, outdoor rated, and they can just kind of dangle before going into your house. But if they're subject to physical damage, then they need to be in conduit. Okay, that makes sense. There's support requirements, every 30 inches, every 12 inches, not as harsh for solar supports, for non-service entrance cable supports. Cables not approved with contact for structure need to have supports every less than 15 feet with 2 inches off of the building. This is a drip loop. The utility's not just making these cables look ugly on purpose. They're arranging it so that water drips off of the cable rather than goes into the home. For overcurrent protection and breaker size selection. So let's say you do your circuit and it's 16 amps and you go it on 20 amp conductor and you find a 20 amp breaker. That's fine. But breakers only come in certain sizes, 15 amps, 20 amps, 25 amps, 30 amps. So what if you calculate the load and it should be 18 amps and then you do your 25% oversizing and your conductors need to be 22 amps? Well, it's saying for breakers under 800 amps, you just round up to the nearest size. Say there's so much selection for breaker sizing at the small level that you can just find the next size breaker up and be fine. You can't, if you need a 30 amp breaker, you can't use a 40 amp breaker, or you shouldn't. But you're allowed to round up to the next breaker size, and it tells you what breaker sizes there are. Sometimes not all these sizes can be found at Home Depot. They might need some advanced ordering if you're doing something odd. Now, when you get over 800 amps, that rounding up to the next size becomes dangerous because the breaker won't trip. If you're ground faulting at 22 amps, the breaker won't trip until you get up to 25 amps. If that was happening at a larger, heavier amperage system, you'd be in trouble. So generally with these larger systems, like if I have a 1400 amp system, I'm still oversizing my conductors by 25%, and that might get me up to 17 or 1800 amps. But because I have a 1400 amp system, then I'm rounding down. And so what that means is on these larger systems, if I'm ground faulting the system capacity into my ground, and my ground is sized for a 1400 amp system, my conductors are sized for more than that, they won't be burnt up until that breaker will open before the conductors burn, provided that it's like a ideal ground fault where the the ground is just going through the circuits and then out to ground through the fault without anything funny going on. Anything funny being like the cables are stripped and touching the roof deck, and the heat from the cables is burning up the roof decks, and that causes other kinds of issues. Let's see, taps. So sometimes with power cables, a power supply, if you're tapping a solar array onto the supply side tap, if you're at any rate, if you're not using breakers, if you just want to land on the power cables directly, tap the cables together, there are certain rules for that. And you can say, well, you can do feeder taps without overcurrent protection if the taps are less than 10 feet long. Generally you're going to have overcurrent protection, at the other side of the tap. Like if you have a distribution panel, well, this is a bad drawing. If you have a main breaker panel here and a feeder conductor here, and then another distribution here, and you're tapping here, you're going to have overcurrent protection where these are landings. It says, well, do you need overcurrent protection here? It depends on if the feeders are really kind of their own branch circuit or not. When you're upsizing conductors, you're not always required, and you're not required to upsize the ground. So if I'm upsizing my conductors because of voltage drop, say, well, it's a 40 amp device and I only need to use number 12, but I want to use number 8 because of voltage drop, and that's 60 amps or whatever it is. Do I need to upsize the drain to the system? Well, there's no more additional power in the system. You don't need to upsize the ground. Let's see, your breakers and panels should not be, your breaker switches should not be more than 6 feet 7 inches up off the floor. So you shouldn't have to climb a ladder or step stool to access a breaker or disconnect switch. A grounded conductor shall not be connected to the equipment ground or reconnected to the ground on the load side of the service except as permitted. Neutrals can only share the same terminal as the ground on the main service panel. So what does this mean? Well, there's service panels where you have your neutral side and you have your ground side, and there's a metal bar that connects the two together. And then there's service panels that don't have that feature. Sometimes you have to enable that feature. Sometimes it comes shipped out of the box. Well, what's the difference? Well, the neutral needs to be connected to ground, but if the neutral is connected to the ground all over the place, well, then power could be leaving the system before getting back to the main, and that would cause, sensing ground fault detection sensing systems not to work. And so if you have a sub panel and you have a main panel, the neutral should be following all the way back to the main panel and not connecting to ground. And your ground should flow all the way back, and then your neutral connects to ground at that point. There are exceptions. If you have a standalone service, the service can have the neutral connected to ground and come off at that point, like a power supply service. But the point is, if you have a load panel coming off a main panel, don't connect neutral to ground at that point. If your solar array is tied in as a load side connection and not on a standalone kind of dedicated panel that taps into the utility conductors, but if your solar array comes into the bottom side of the bus bar on a load panel, you might read something in code that says connect it, make sure that the neutral is connected to ground. Don't doubly connect it to ground. Make sure it's only connected to ground at one point, like it is on an existing facility. So that neutral point to ground that gives the neutral its 0 voltage reference is called the main bonding jumper. And you don't want that main bonding jumper to be occurring at multiple places on the building, because then your voltages, your neutrals could have a 0 voltage reference and not have their ground fault detection work. Let's see. Parallel conductors should not be smaller than 1/0 cables. That's a common electrician exam quiz question. Is if you have conductors, ground conductors, power conductors, and you want to say, well, these conductor cables are so thick that I want to do parallel runs to make the installation easier, you can do that, but the conductors of those parallel runs have to be 1/0 or larger. So smaller wire sizing, you're not allowed to do parallel runs. You're allowed to design some equipment with small parallel runs and then go get it UL listed and provide an assembly, and everything inside that listed assembly, you have that UL listing for. You're not allowed to design, un-UL listed systems of your own design and do parallel conductors for ampacity sizing for anything smaller than 1/0. Main bonding jumper. Where a main bonding jumper and a system bonding jumper is a screw only, the screw should be identified with a green finish and be visible when installed. So sometimes you'll take that neutral bar and you'll say, okay, well, the back of this box is connected to ground. And to connect the neutral to ground, you'll take a green screw and you'll screw it into that back of the box to make the jump between neutral to ground, as if this were a standalone box. But we're not doing it here because this box is actually off a sub panel, and in that sub panel, they already have a neutral to ground connection. So that's kind of the main rule of thumb, is when you have sub panels off a main panel, does that don't put the neutral to ground in the sub panel. If it's a standalone kind of supply side tap service, then you can do it there, but not off an existing service. You only want to have one neutral to ground connection. Let's see. So we already saw that slide. The green screw slide we already saw. What I would say is there are this stuff about separately derived systems is your buildings are going to share the same ground and grounding electrode conductor. Sometimes when you have separate backup power systems, you don't want them to share the same neutral. So if they, so if you disconnect the existing system's neutral, what you swap it out with, whatever your backup system that has its own neutral, that neutral also has to be connected to ground. So that neutral needs its own neutral to ground connection. But if you're not disconnecting the neutral from the utility or building side, and you're carrying that neutral through to your backup system, then you shouldn't have a second neutral connection to ground. I would recommend going ahead and getting 3-pole switches, because sometimes, like on one-way battery inverters, like battery backup UPS systems that don't backfeed the grid, they can't operate tied into the utility neutral. So getting a 3-pole disconnect switch for your hot, your other hot, and your neutral, even if you don't use the pole that's intended for neutral, you'll have it there. So you can get 2-pole disconnect switches, you can get 3-pole disconnect switches. I'd recommend just getting the larger 3-pole disconnect so that you don't screw yourself in the end. In fact, I would get fused 3-pole disconnect switches so that you can so that then you can put an inline automatic Or really, if you just do a standard 3-pole disconnect switch with an inline automatic transfer relay, that would be how you get your automatic transfer plus your manual transfer. So you're this is just keeping talking about the neutral, which is called a grounding conductor, not being connected to the grounding electrode. The equipment ground system should tie into the ground. The neutrals should tie into the neutrals. There should only be one point where the neutral ties into ground. Otherwise, those breakers won't work. The actual grounding bar themselves can be a ground rod or a ground plate. Generally, these things have to go, they're 8 feet and they go, all the way into the ground. You see this little clamp that connects the ground rod to it. But there's different rules based on how conductive that ground is. Concrete is less conductive. And so there's more material that has to be making up this ground than without concrete. If your ground is too hard to drive that bar in, there's other ways to do it. You can circle the building in copper. So there's ground rods, ground plates, ground ground rings. The general one is to use a ground rod. Different soil types, driving in that ground rod can be in a very easy job or a very difficult job. The general rule is that your whatever ground load your system is using should have 25 ohms or less resistance to ground. There's a specific instrument called a meter test that you use to verify resistance to ground. Certain soil types, very dry, sandy soils, may not have that resistance to ground. You may have to put in additional ground rod. Kind of getting towards the end of our time here. So I want to show you what's in the rest of the program so that you can thumb through it with ease. When not exposed to physical damage, a number 6 ground is permitted to run without protection. Otherwise, it needs to be physically protected. So in solar, that grounding electrode that needs to go all the way up to the rail on the rooftop, the smallest size is number 8. But if you make it number 6, you can just run number 6 bare copper up to the roof and tie off on it. I always use a number 8 because I tuck this grounding electrode conductor. I include it inside the conduit of my pre-built cable, MC cable. And so I actually select my MC cable knowing that I have to run a number 8 ground up to the rooftop. So I select number 6 MC cable, which comes with an undersized ground. That gets me my number 8 ground up to the rooftop. Essentially the grounding electrode conductor system needs to be continuous across its run. So wherever it starts to wherever it finishes on that final ground lug or ground screw, you should not have any crimps within it. Let's see. So if you're doing concrete encased grounding electrodes, the wiring has to be a little bit larger to that electrode. Normally, you're dealing with number 6, whether it's a rod, pipe, or plate. No larger than number 6, but particularly with concrete foundations where you're using the rebar of the concrete or putting a ground rod into that concrete, you need to use something slightly larger because that concrete is less conductive than normal soil. And so depending on your size of your electric service, you can have really small equipment grounds, but the smallest is number 8. Solar, what size of a ground you need to run up to the rooftop, the smallest size is number 8. At this point, we are at the end of the program, And we're really only almost done with 250, and we still have section 300 and 400 to go through. So, first time program, I thought I could get through this a lot more quickly. I'm going to probably have to keep making the rest of the recording for you to preview in your whole time. It's not going to do us any benefit to rush through it. But let me just preview what the rest of this program is. So you're going to get your 2 hours of credit. If you want to come back to it, you can. But basically what the rest of the discussion is we'll talk a little bit more about grounding sizing and equipment ground sizing. Just to kind of jump up and down on saying you just run number 8 up to the rooftop, or number 6 if you're not in conduit. The section 300 of code gets into wiring. And so we're talking about how to wire through a home, how to wire underground, and how to wire within a raceway. So when we're wiring within a raceway, whether it's a metal raceway or a plastic raceway, and how to route the grounding through that comes to a matter of like what bits and pieces of conduit design are you using? Are you using the conduit as a ground path or not? Temperature becomes an issue as well up on a rooftop. So we talk about how conduits and conductors are adjusted for temperature and how to read the temperature adjustment tables. So we'll leave that for detailed discussion. We're just trying to get through the summary right now. There's ampacity adjustments for putting more than 3 cables into a conduit. The cables themselves heat up and require additional ampacity correction. Different cables have different temperature ratings. And so what adjustment factor you use is based off what material you select and what the material temperature rating is. Higher rated temperatures have less derating than lower rated materials at lower temperature ratings. In something like solar, you're generally dealing with high temperature ratings, but if you're using off-the-shelf parts from Home Depot, you're dealing with lower temperature ratings. And so which temperature level you do your calculation at adjusts these fudge factors. We'll talk about that later. But there's different charts for like cables in conduit, cables in free air, cables in raceways, and it'll just be charts and charts and charts, but just different, ampacity derates for different wiring scenarios. Finally, we get to charts that actually go through all these acronyms that electricians and engineers love, and it turns out they all mean something. The W indicates a wet rating. The -2 is indicating a kind of a outside of conduit, more robust exposure to sunlight rating. So all of these things matter, and they all drives the insulation thickness. Really non-dry only cable has a less thick cable jacket than your underground service entrance or underground feeder cables that have thicker jackets. So all of these acronyms and product selections mean something. Some more spacing requirements. Talk a little bit about bodies, but basically you use conduit bodies to make wire pulling easier or to make the project look better. You're allowed to splice inside raceways and conduit, but only if you have enough space. You don't have enough space in these smaller conduit bodies. We talk about metal clad cable in other classes. We'll talk about it later, but this is the MC cable. This is what I use for DC runs inside of homes, and even tucked out just through the attic. So we talk about metal clad cable, a couple of other different types of cable. Finally, we talk about auxiliary gutters, what you can do in it. Sometimes it's a lot easier to put in a gutter right before your equipment to do some cable management and routing, and make your runs look better than just putting into conduit all the way to the equipment. And we talk about some nuances of weather exposure. The main thing with weather is that there's weather rated devices, fittings, couplings. You know, you can have EMT conduit with an EMT connector, but there's also a rain tight EMT connector. And most of the time, EMT is not used in outdoor construction work. You're dealing with more robust, rigid conduit, concrete encased raceways, more weatherproof, weather-tight things. And so these specialty pieces like rain-tight EMT couplings, you don't find at Lowe's or Home Depot. You have to get at an electrical supply store.